Dynamic Memory Allocation, DMA, in the C programming language is a powerful mechanism that allows memory to be allocated, resized, and freed during runtime. Unlike static memory allocation where the memory size is fixed during compilation. This feature is essential for creating flexible programs capable of handling unpredictable or variable amounts of data. In a typical C program, memory is divided into segments such as the code segment, global, static segment, stack segment, and heap segment, with the heap specifically used for dynamic allocation. The C standard library, through the header file _stdlib, h greater than, provides 4 key functions: malloc, calloc, realloc, and free, to manage this heap memory. The malloc function allocates a specified number of bytes and returns a pointer to the beginning of the block, but it leaves the memory uninitialized. In contrast, calloc allocates memory for multiple elements and initializes the entire block to 0, whereas realloc modifies the size of an already allocated block, either expanding or shrinking it while preserving existing data when possible. Once dynamically allocated memory is no longer needed, the free function releases it back to the system to prevent memory leaks, which are among the most common issues when using dynamic memory. The concept of dynamic memory allocation is deeply connected to several memory allocation models that explain how memory is organized and managed internally. Static allocation assigns memory at compile time, and stack allocation manages memory automatically in a last-in first-out manner. But neither provides the flexibility of dynamic allocation through the heap. Heap allocation is the primary model for DMA, where memory is managed using free lists, block metadata, and headers. Beyond this basic model, more sophisticated system-level memory models exist. The single contiguous allocation model provides one large block of memory for an application, but it is outdated and inflexible. Partitioned allocation models divide memory into multiple parts, either as fixed partitions, leading to internal fragmentation, or variable partitions, which offer flexibility but may cause external fragmentation. More advanced models include the buddy memory allocation system, which splits memory into blocks whose sizes are powers of 2. This system allows efficient splitting and merging of memory blocks and is widely used in operating systems such as Linux. The slab allocation model, also popular in OS kernels, allocates memory in predefined slabs that contain objects of identical size, reducing fragmentation and improving performance. Pool allocation, or object pooling, divides memory into small blocks of equal size and is commonly used in embedded systems, real-time applications, and network software where speed and predictability are crucial. Although C does not include built-in garbage collection, custom memory managers can be implemented using garbage-collected models such as reference counting or mark and sweep techniques. Dynamic memory allocation also brings challenges such as internal and external fragmentation. Internal fragmentation occurs when the allocated memory block is larger than what the program actually needs, while external fragmentation arises when free memory is split into small scattered pieces that cannot be used for larger allocations. To manage these issues, heap managers use allocation strategies like first fit, best fit, worst fit, and next fit. First fit assigns the first sufficiently large block it encounters. Best fit finds the smallest suitable block to reduce waste. Worst fit allocates the largest available block to minimize the creation of small leftover spaces. and next fit improves first fit by continuing the search from the last allocated position. Dynamic memory allocation is indispensable in real-world programming because it enables the creation of dynamic data structures such as linked lists, trees, graphs, stacks, queues, and hash tables. It allows programs to efficiently handle data that grows or shrinks during execution and is vital for building complex software like operating systems, compilers, device drivers, and real-time applications. However, improper use of DMA can result in severe errors, including memory leaks caused by not freeing allocated memory, and dangling pointers, which occur when memory is accessed after being freed. Double free errors, uninitialized pointer usage, and incorrect pointer arithmetic can also lead to crashes and undefined behavior. Nevertheless, when used correctly, dynamic memory allocation provides unmatched flexibility, efficiency, and control over memory usage. It remains one of the most important concepts in C programming and forms the foundation for understanding low-level memory management and advanced computer system design. Mastering dynamic memory allocation is essential for programmers who want to write robust, efficient, and scalable software that interacts directly with system resources.